This is a video about tension, and it tries to fill in some of the gaps left by other videos you may have seen. First of all, let's deal with what tension actually is. If you have two objects that are in contact with each other, they can exert a force on each other, and those contact forces have different names based on the types of objects they're in. So let's have a look at this. If I draw myself a table, and onto that table I put a box. To that box I attach a rope, which is going to be pulled along by a hand. If I was to look at the forces of tension caused in that rope, now when I deal with tension in a rope, I like to imagine I can zoom in on a bit of it. So let's imagine I can zoom into this part here where I've just drawn the red line. And when I do that, I'd like to imagine I can see like the individual molecules, and those molecules will be connected together with some type of bond. I'll represent that as a spring. Now, as I stretch the string, these molecules move further and further apart, and I like to then view the tension as being the force or the electromagnetic force that tries to pull those molecules back together again, which I'll show here on my diagram. Now what this break in the rope here allows me to do is the following. If I wanted to consider what was happening from the box's point of view, then from the box's point of view I could consider all the way up to the break in the rope here, like this. And so this here would just become the stuff that I would need to worry about if I wanted to see this from the box's point of view. If I wanted to see this from the hand's point of view, I would consider everything up to the break there, and I could say, well, this is what the hand would see. Let's try and give you some examples of that. Let's have a look at my first example. In this example I have a 2 kilogram block, and the force of that resting on the table will produce 2G acting downwards. Because it's resting on a table, there's that force that stops it going through the table, which is this normal reaction force here. I've got a couple more forces to consider. I've got some friction in this one, which is 4 newtons, and I've got a block being pulled in this direction, and I know that because of my acceleration up here. And because I'm connected by a string, which I'll highlight in blue, to my hand, I've split my rope down here and I've drawn in my tension forces either side of that. Removing all the highlights, I want to work out, for my first part of the question, the tension. Well, everything I've got is connected to the block, all the information I've been given. So I'm going to be just considering it from what the block sees, which is all the way up to my break line in the rope. So I'm looking at all of these forces. Now when looking at solving a tension problem, you really need to use Newton's second law of motion. In other words, the F is equal to ma. That's our main strategy for being able to solve what's going on in this. So if I resolve horizontally first, because lots of my forces are acting in the horizontal direction and the force of tension is in the horizontal direction, I would take this idea, F equals ma. Now the biggest direction, the direction which is moving in, so the biggest force will be the tension, and then that will be being slowed down by the friction to 4 newtons. So that's what my overall force is acting horizontally. My mass is 2 kilograms and my acceleration is, I put in brackets, 2 meters per second squared. So nice bit of simple maths on this bit. 4 add 4, final tension will be equal to 8 newtons. If I look at part B, I'm just asked to find out the force of Y. Now this doesn't really have anything to do with tensions, this is just resolving vertically. So I look at all the forces acting upwards and downwards. I have the force of it going upwards is balancing the force of it going downwards. Now I know that because there is no acceleration of that particle. And in this case gravity is equal to 9.8. So 2 lots of 9.8 make 19.6 newtons. Now you'll find these on page 163 Example 6. Now this question is more commonly drawn like this. We take our box, we rest it on a table, and this force here to the right may or may not be written as a tension, but most books won't have this bit shown in because they don't tend to show the hand here. And so they will just show you what's highlighted in this blue box here. Just go around in green, which is what you see in the questions in the book. This is an example of a connected particles problem. So you've got two particles connected by some string. We're told that there are two particles, P and Q. Here's particle P and here's particle Q. They've got masses of 5 kilograms and 3 kilograms respectively. Here's my 5 kilograms, here's my 3 kilograms. They are connected by a light inextensible string. This is my light inextensible string here between the two. And particle P is pulled by a horizontal force of magnitude 40 newtons. This is my magnitude of 40 newtons. And it's being pulled along a rough horizontal plane. Particle P experiences a frictional force of 10 newtons. So particle P is experiencing its frictional force of 10 newtons, and particle Q experiences a frictional force of 6 newtons. Here's Q, and here's its 6 newtons that is slowing it down. In part A, I'm asked to find the acceleration of the particles. So what I've done here is I've highlighted in blue all the horizontal forces that are to do with particle Q, and in green I've highlighted all the horizontal forces that are to do with particle P. Let's have a look at this now from the point of view of Q. So if we resolve horizontally, and we use our strategy again of F is equal to ma, Newton's second law, we know our particles are moving to the right. So that must mean this tension here must be bigger than the frictional force of 6 newtons. So when doing the force is equal to mass times acceleration, we put our biggest force first, which is the tension, and we take away from that the forces that are counteracting that, the friction. Now that's equal to the mass of the particle, 3 kilograms, multiplied by its acceleration. When we look at what happens from particle P, again using our strategy of Newton's second law, F is equal to ma, and you kind of always jump back to that when you're looking at tension, we can see the 40 newtons must be bigger than the tension and the 10 newtons. So we put our biggest force first. Remember, the biggest force is the direction it's moving in, and then we take away from that the forces opposing that. The mass of this is 5 kilograms, and that's my acceleration. Brief tidy up. Now if we look at my two equations, and if we were to add those two equations together, you'd see that the negative part would cancel out with the positive part, just giving me an equation in A. And as I'm asked to find the acceleration, that seems to be a good way to go ahead. So equation 1, add equation 2. Will give me 30, take away the 6, 8a, so 8a equals 24, therefore final answer. For part B, we're asked to find the tension in the string. Well, here's an equation with tension in, which we've already done. We know what the value of A is, so we just chuck the value of A into here and then solve it. So for part B, job done. Now let's go back and just review some stuff. When we formed our equation, notice that we had two variables in our equations. Two variables, two equations, the tension and the acceleration. So when we were looking at our equations, I found that by adding them together, I got myself an equation with just one variable in it, and so therefore it means it's solvable. Remember, if you've got two unknowns in your equations, then you must always have two equations to solve it. Okay, moving on to our next question. This one's taken from page 174, example 14 of the Year 1 Mech book. Let's have a look what we've got. Two particles, A and B. Here's A, here's B. They have masses of 0.4 kilograms and 0.8 kilograms. I've just written those in. They're connected by a light inextensible string, which will be this one, and it goes around a pulley down to here. We're told that particle A lies on a rough horizontal table 4.5 meters from a smooth pulley. So I now know that the distance between A and the pulley is 4.5 meters. And the smooth pulley, which is fixed at the edge of the table. The string passes over the pulley and B hangs freely with the string taut 0.5 meters above horizontal ground. So let's put that distance in. I usually do some lines like this to indicate a solid surface. A frictional force of magnitude 0.08 g opposes the motion of particle A. Well, here's my 0.08 g. It's worthwhile noting it has to be over here because particle B hangs freely, so there's no friction involved there because it's not in contact with another surface. We've been told that our pulley is smooth, so that can't cause any friction. So the only friction we can get is between the two surfaces where A and the table meet. We're told that the system is released from rest. Find A, acceleration of the system. Now with a pulley style question, we need to get our tension into the strings. So whenever you have a pulley involved, you need to have a rope break before the pulley so you can put your tensions in, and then you need to have a rope break after the pulley so that you can put your tensions in. Let's have a look at forming some equations. From the point of view of A. So I am considering now everything from A all the way up to my rope break. This is essentially what A sees. Same strategy involved for our tension problems. We use Newton's second law, F is equal to ma. I know that A is moving in this direction. Because of that, this force here, this tension, must be bigger than this frictional force. So using those to help me, tension, take away the frictional force of 0.08 g, must be equal to the mass of the object, mass of A, multiplied by its acceleration, which I don't know, so I'll call it A. Let's consider now what happens with particle B. Well, these are all of the forces that B gets to see, all the way up to the rope break. Because it's moving in this direction, that must mean the force in that direction must be bigger than the tension in the opposite direction. Using our strategy again of Newton's second law, starting with our biggest force, the one which it's moving in, 0.8 g, take away from that the tension which is operating in the opposite direction must be equal to the mass multiplied by its acceleration. Remember, we are trying to find what the acceleration of this is going to be. So if I take my two equations and I add them together, again we see that this negative value of t will cancel out with this positive value of t here. Adding the two equations together, I get putting in the value of gravity as 9.8, given my acceleration as 5.88 meters per second squared. Now often you will see this type of problem in a book solved as follows. Here's my table, my smooth pulley, my light inextensible string connecting them together, and the forces of tension would just be as shown, without this rope break in them. This leaves you at a disadvantage when you're asked to consider the forces on the pulley, because you're actually missing out these forces here. So if I was to go ahead and show you how I would do that, let's add an extra bit. If I consider the forces acting on the pulley, that's going up to my rope break here, and it's also going up to my rope break here. So it's all the forces inside that green box. If I have a look at the forces around my pulley, so there's my pulley, here's my rope, here's my tension up to this point, going up to the rope break, there's my tension there, and I look at adding those two vectors together. Remember, when you're adding your two vectors together, they need to go from the start of the vector to the finish of the vector. So if I called that start and that finish, and then I added on another vector, that would go from that start to that finish. Sometimes it's called nose to tail. So let's have a look at how I would add these vectors together. So if that was the start, that was a finish of that vector there. Let's draw that down. Start to finish. Let's look at my next vector. This force acts in this direction. Here's your start, here's your finish. Remember, we want the start to finish, So I could put my start here at the end of this one and my finish over here. And my resultant vector would be this one here. That would go in that direction. Out of interest, we have a right angle triangle here. So we could just go ahead with Pythagoras and we'd find out if this was t and this was t, t squared plus t squared is 2t squared. The square root of that would give me the square root of 2t squared. And how would I find t? Well, I would get that because I know the value of the acceleration here, and I can put that into this equation here to solve it to find t. Multiply that by the 2, then by the t squared, then square root the whole thing, job done. So that would give you the forces acting on the pulley. Moving on to my next example, page 173, example 13. This time we've got our pulley system and most of it's set up for us. We've got two particles P and Q. Here's particle P, here's particle Q. They've got masses 2m and 3m, 2m, 3m. They're attached to the ends of your light and extensible string. The string passes over a small, smooth, fixed pulley and the masses hang with the string taut. The system is released from rest. Then we're looking at writing down an equation of motion for P and write down an equation of motion for Q. Right, before we get into that, let's have a look at what else we've got. The acceleration is in this direction, which must mean that this force has got to be bigger than this force so that the whole system can move in that direction. We can also see my rope break here before the pulley and my rope break here after the pulley with my tensions highlighted in there. So let's have a look at A1. Write down an equation of motion for P. Now, an equation for motion doesn't have to be something from the Sudat formulas. It just has to be an equation that involves something to do with how it moves. In our case, we can get acceleration really quite quickly from this one. We would get that from Newton's second law. Let's look at this from the point of view of P. We're going to resolve this in the vertical direction using Newton's second law of motion. From P, we go all the way up to our rope break, like that. Everything in that box is what I want to play around with or consider. So using force is equal to mass times acceleration. This has got to be bigger than this force here because it's moving in the direction of the biggest force. So from our forces, biggest force first, take away the smallest force. That must be equal to its mass times by the acceleration, which we're going to call A. I've got my first equation that's got something to do with motion, in other words, our first equation of motion for P. For my next part. So, for my next part, write down an equation of motion for Q. Here's Q, so I want everything in this blue box here. It's moving in this direction, so the downward force here must be greater than the upwards force here. So again, I'm resolving horizontally, and again using Newton's second law. So the biggest force goes first, and I've got my equation now, which involves something to do with motion, so I've got my equation of motion. On B, I'm asked to find the acceleration of each mass. Well, similar to how I've done it before. Positive tension here, negative tension there. Add equation 1 to equation 2. Simplify and divide through by m. Final answer. And part C, find the tension in the string. Might as well use equation A for that. I can't go any further than that because I don't know the value of m. And for part D, find the force exerted on the pulley by the string. Resolving vertically for this one. I know my tension from the previous question. Final answer. Okay, let's have a look over what we've done so far. Right back at the beginning, we looked at having a block being pulled by a piece of string. And on this bit, I introduced you the idea of the rope break. Moving on from that, I then showed you the idea that Newton's second law of motion, F is equal to ma, is a really popular strategy for solving any problems involving tension. Once we'd had a look at one particle connected with a string, we then naturally progressed on to two particles connected with a string. Again, we see the idea of a rope break. And again, we are seeing the idea of Newton's second law being used to form our equations. Moving on from two particles connected with a string, we then go to two particles connected with a string but with a pulley involved. And now I wanted to show to you the idea that when you have a pulley involved, you have a rope break on one side of that pulley and a rope break on the other side of that pulley. Interestingly, this is one of the few cases in mechanics where you will have horizontal forces on one side of the pulley being equated to vertical forces on the other side. Essentially, a pulley changes the direction of the forces. Moving on from this one, we also see again the similar ideas of using Newton's second law to try and solve problems involving tension. Moving on to the last example, again we have these common ideas of our rope break introduced on both sides. We see Newton's second law of motion again being used to solve the problems. And finally, you can see how the movement in here has been changed from going up to going down because of the effect of having a pulley there. Well, hopefully that's improved some of your knowledge to do with tensions and pulleys. More information on this can be found on chapter 10. Thank you.